Is this better? Yeah.
Okay, very good. Our second paper is about reducing ambiguity in example-based synthesis using additional input-output relations. And Roopsha is here. She's going to present the paper.
Thanks, Mohsen. You gave a good summary of this talk. So I'm really excited to present our work on augmented example-based synthesis, which is joint work with Shengwei An, a graduate student at Purdue, Rishabh Singh, who should be here in the audience, and Sasha Misailovic. So classical program synthesis, as I think many of us know, seeks to generate programs from what Manna and Waldinger back in the day like to call dreams. But unfortunately, what is really expected is that you dream up a complete formal specification of the program's expected behavior, which, for instance, if you want to compute a maximum of 3 integers, I think there is a might look something like this, right? Now, I trust that the average person in this audience may indeed dream up such this beautiful specification, but the average human and in fact the average programming enthusiast may not, right? And there has also always been this debate in classical program synthesis about whether it's actually easier to come up with this specification than to actually write down the program. So example-based synthesis seeks to essentially address these issues with the specification problem in classical program synthesis, and also more ambitiously to democratize programming by essentially only requiring the user to provide examples of the expected input-output behavior of the program. Okay. So for instance, for this max problem, the user might say that when the inputs are 0, 10, and 2, the expected output is 10, and so on. Right. Now, hopefully, we'll all agree that this is certainly easier than writing the program, and this task can be accomplished by non-expert users who may not be able to write programs or certainly not complete formal specifications. So let me actually just clarify at this point that in PBE and in general in many paradigms in program synthesis, we like to view the synthesis problem as a search problem with an associated search space that might be defined using a grammar or a DSL or a partial program. But I'm not going to explicitly identify this search space unless absolutely needed on my slides, okay? But there is one. So PBE sounds promising, but unfortunately, there can be many different programs that are consistent with a set of examples, because this is a highly incomplete specification, and this is referred to as the ambiguity problem in PBE, right? Also, and quite obviously, many of these programs that are consistent with these examples may not exhibit the implicit intended behavior on unseen examples, right? Or may fail to generalize to unseen examples. And this is what I like to call the generalizability problem in PBE. So I think I need to just stand here because this is not working great. So how do existing solutions address these issues? Well, they either place a syntactic bias on the search space through highly structured and domain-specific DSLs or carefully learned ranking functions, or they might employ a user in the loop and ask the user to validate candidate programs or abstract representations of examples, or might just ask the user to answer questions like in active learning. Okay. So the problems with these existing solutions is that they are too domain specific, so they take a long time to develop and they are hard to translate to other domains. They place a heavy burden on the user in many cases, thereby going against the spirit of PBE. And finally, ultimately, even after all this, they can still be inadequate. So we present a new approach to example-based synthesis that really augments all of these approaches. So it is portable across multiple domains and synthesizers and can be used in conjunction with existing synthesizers and techniques based on, DSLs, ranking functions, and so on. Our solution also incorporates different user interfaces that engage the user to varying degrees of engagement. And finally, our evaluation results are really promising, and I can't wait to share them with you. But let's go through our basic idea first, which is essentially to augment PBE by placing a semantic bias on the search space, in contrast to the syntactic bias that existing solutions have been placing on the search space in order to address the incompleteness issue of the specification. Okay. So, for this max problem, for instance, how might we place such a semantic bias? Well, while there can be many different approaches, what we say is, suppose we have an oracle that tells us that this program that we desire our synthesizer to generate is permutation invariant. Okay, that its output does not change when the elements of its input are permuted. So, given this, it is quite easy to apply this property to the given set of examples by essentially permuting the inputs for each example and keeping the output unchanged, and generating a larger augmented set of examples. Okay, thereby, in fact, placing a semantic bias on the search space, which in this case is actually adequate to eliminate that incorrect program. Okay. So, more generally, permutation invariance is an instance of a broader class of relational properties that we call relational perturbation properties, that relate the change in the program output to the change in the program input. Okay. And we have a fairly general formulation for this class of properties that is parameterized by an input perturbation array and some parameters k1 and k2 that together essentially enable you to compute the output perturbation. Okay. I'm not going to dive too deep into this formulation, but I just want to tell you that this subsumes, of course, permutation invariance, but many other interesting properties like permutation preservation, where you might say that if the inputs are permuted in a certain way, the output is permuted in the exact same way. Okay. Or value preservation, which says that if you apply an affine transformation to all the inputs in your to all the elements of your input, then the output is modified by the same affine transformation, and so on. So, notice that this formulation actually subsumes both perturbations that are structural, that change the positions of the elements like permutation, as well as perturbations that are value based, like applying affine transformations to the values. Okay. So, the special formulation of these relational properties makes it really easy for us to, given a certain relational property R, take a set of examples E and apply this property to the set of examples to generate what we call an augmented set of examples or a perturbed set of examples. Okay. So, now that we know about relational properties, these relational perturbation properties, I can essentially give you my our simple two-step key strategy, which is to augment a set of user provided examples using these relational perturbation properties, and then simply use an existing PBE synthesizer with the augmented set of examples to generate a program. Okay. So, now let's take some time off for some Q&A. So, hopefully some of you might think, is this similar to data augmentation in machine learning? And this was referred to in the keynote yesterday by Martin, and where essentially image classifiers seek to develop techniques that generalize better to unseen inputs by applying transformations to existing image data sets that increase their training data set. Okay. So, they might apply various kinds of perturbations to images. So, sure, in spirit our technique is certainly similar to this idea of data augmentation. That is what we are doing. But of course, we want to learn from a very small set of examples as opposed to a large training data set, and this essentially establishes a very different set of problems. Also, our domain and perturbation properties are different. For instance, we are not limited to perturbation properties where the label or the output stays unchanged, which is the case, for instance, in perturbations applied to images, right? We allow the outputs to also change in some predictable way when the input changes. So, couple of more questions that that you should probably hold off because I'm not going to answer them right now. So, given these relational perturbation properties, why are we generating more examples? Shouldn't we be formal and try to enforce these properties in our synthesis? Or why not? Can we use arbitrary relational properties? But I'm not going to answer them right now. So, maybe you can ask me later. The question I want to answer in the rest of my talks, which is also something you should have thought about, is where do these relational perturbation properties come from, right? That is really the main question to answer now, since, as you saw, our key strategy is really simple. So, as I said, we have different user interfaces that engage a user in different ways. So, in fact, we have 3 different user interfaces. The first one is the property selection UI, where we have the user do more of the work. Okay, so the user selects a set of applicable properties from a finite set of properties. And by the way, I know I presented a parameterized formulation that essentially corresponds to an infinite class of properties, but not all of those properties are interesting or even necessary. So, we restrict our attention in this work to just a finite set of properties. Okay, so the user only needs to pick some properties from a finite set of properties. Now, given that the user does all this work, that the work that our augmented PBE engine, which is this little white engine, needs to do, given an existing PBE engine in this gray box, is simply for each property implement our key strategy, which is to perturb the examples according to that property, generate an augmented set, and ultimately call the synthesizer using that large augmented set of examples and ask the synthesizer to compute a program. Okay, so this is very straightforward, but you might ask, rightly so, that isn't this too much work for the user, for a non-expert user to pick applicable properties? And so, in our second UI, this white engine essentially only asks the user to validate or invalidate some perturbed examples for each property. Okay, and if the user does validate some of these examples, then the white engine assumes that the property holds and then just proceeds as before. But you might be hard to please, and you might say this is still too much work. And so, we do have a third UI where all the user has to do is to just provide input-output examples and nothing more. Okay, just like in the standard PBE setting. So, now this little white engine does have to do a lot of work. It has to, our intention here is to try and automatically infer a set of a maximal set of properties that are consistent with the definition of the synthesis problem. Okay, and how might we do that? Well, we can cast this as a partial max SMT problem, where which accepts essentially a set of hard constraints and a set of soft constraints, and then tries to generate a solution where all the hard constraints are satisfied and the soft constraints, and tries to maximize the number of soft constraints that are satisfied. So in our context, if the set of hard constraints essentially correspond to the user provided examples, and each soft constraint corresponds to the perturbed examples for each property, and we ask the synthesizer to synthesize a program that satisfies all the hard constraints and maximizes the number of satisfied soft constraints, then we have what we wanted. We will have the synthesizer generate a program that maximizes the number of properties that are applicable in this synthesis setting. Okay. So, this is essentially a hypothesis, and we need to check this out in our and we do that. We have an extensive evaluation that I'll summarize here briefly, but I invite you to look at the paper some more. So, we instantiate our framework for this evaluation with the Sketch general purpose program synthesizer, and our engine is called Sketch AX. It's not a super imaginative name, it's Sketch with augmented examples. Okay, and we have a whole bunch of benchmarks that are drawn from Sketch repositories, and then this conditional linear integer arithmetic crack of the annual syntax guided synthesis competition. And our domains essentially include scalars, arrays, and matrices over booleans and integers. Okay. Now, each of these benchmarks comes with a partial program, and this is important. It comes with a reference implementation or a complete functional specification, not to do the PBE, but to help us evaluate the success of our technique. Okay. And this really restricted where we could draw our benchmarks from. And our finite set of properties for the experiments is essentially restricted to a set of 8 properties that includes all of the properties we've seen before and some more. So, first, I want to show you the success rate of different synthesis engines for benchmarks that do satisfy some properties. Not all of our benchmarks satisfy any of these 8 properties. Okay. So, what do I mean by success rate? For each benchmark, we execute 10 runs, where each run uses a different randomly generated set of 3 examples drawn from the reference implementation. Okay. And we see how for over those runs, how many of these instances actually satisfy the specification. Gray is baseline sketch, pink is sketch AX with the property selection UI, where the user selects the property. Blue is the property validation UI, where the user just validates perturbed examples, and green is the cool interface, where we automatically infer properties. So, the first thing I want you to notice is that the success rate of the property validation UI, and more significantly the property inference UI, matches that of the case where the user selects the properties. Okay. So, this really establishes confidence in our inference algorithm. And I also want you to notice that this provides a 60% improvement in the baseline, in the success rate of baseline sketch. So, that's for properties, benchmarks with properties. The improvement is more dramatic if we zoom in on benchmarks that are over bit vectors. Here, sketch does not perform well, too well at all in the baseline case. It's just a 30% success rate. We have been able to improve the success rate to close to 90% with an improvement of essentially 191%. So, on this last graph, essentially we have all of these success rates for different categories of benchmarks, and I want you to notice that when benchmarks do not satisfy any properties, even then we do not hurt the success rate of baseline sketch. Okay. So, our property inference engine is doing what it is supposed to do. So, an overall success rate is about 22%. So, that is it. That was augmented example based synthesis. We do want to explore and extend this idea to other domains, other PBE engines, and other classes of properties. And given this really promising proof of concept, we do want to try and explore the possibility of developing new synthesis algorithms that exploit relational perturbation properties in their search procedure itself. So, that's it. Thank you.
Very good. Questions, please? You have a question.
Right, thanks. That was very interesting. From a sort of methodological point of view, what steps did you take to make sure that the choice of benchmarks for evaluating your tool didn't sort of affect the design decisions in your heuristics in your tool?
This is a really good point, and to be honest, we were really surprised that this hypothesis of ours in the third UI, which tries to maximize the number of properties that are consistent, actually held out that well. And this is definitely an effect of the domain itself. So, what we also did was so a max assembly solution can have multiple solutions. Okay. And so, what we did is we learned a ranking function from our class of benchmarks to essentially rank the sets of properties to try and see if that made a difference. And in this case, it did not. So, a randomly picked solution from that maximal set of properties was actually adequate. So, what this indicated to us is that the partial programs that essentially already place a certain syntactic bias in this domain, essentially prevent the inference of arbitrary properties or properties that do not hold in general. But we do have a method to develop ranking functions tailored to certain domains that we think will be more useful in other domains.
So I'm curious what other domains that you're considering. So for example, do you think these properties and this technique generalizes to, say, algebraic data types?
So I think so, but we are just beginning to think about this, and this is definitely one of the domains that we would like to explore. We have thought a little bit about strings, and those are hard because again there are really, I mean, the synthesizers for strings, for string manipulating programs are already highly tuned, and it's unclear whether there are interesting semantic properties that we might be able to enforce in that domain. But yeah, algebraic data types in general might is certainly a domain of interest.
Maybe a quick question. We have to move on.
So the once you apply the relational perturbation properties, the resulting program, the synthesis of the resulting program depends on whatever tool you offload it to, right, or whatever in underlying engine you have. But your relation might not have finite orbit. And so is it possible to do some require something algorithmically from the underlying synthesis engine in order to make some guarantees such that it's, I don't know, well behaved modulo the relational perturbation properties at least on your input domain, even if it has infinite orbit?
So do I have time to answer this question?
Yeah, maybe.
Okay, so the quick answer is
Quick
we
answer.
are actually not trying to first formally enforce these properties, right? Even if we learn some examples that actually hold in this setting, even when the property does not hold over the universally quantified domain, we still actually can place a semantic bias and improve our success rate. And so because we are staying true to the spirit of PBV and not trying to really enforce properties, this is not as much of a problem. But we can talk further more.